Hi, and today we are gonna see how will be the temperature profile when the slab is maintained at equal surface temperature. So equal surface temperature in the case of slab. So we know the general heat conduction equation in the Cartesian coordinate system is kx times w/t by w(x) square plus ky times w/t by w(y) square plus kz times w/t by wz square plus q dot is equal to rho Cp times the change in temperature with respect to the change in time. If you don't know this equation, then watch my previous video where I have derived the general heat conduction equation in the Cartesian coordinate system. So if the material is isotropic, that is, the property of material remains same or equal in all directions. So if the material is isotropic, then the thermal conductivity K will remain same in x direction, in y direction, and in z direction. So we can write this equation as w/t by w(x) square plus w/t by w(y) square plus w/t by wz square plus q dot by k is equal to rho Cp by k, the change in temperature with respect to the change in time. So w/t by w(x) square plus w/t by w(y) square plus w/t by wz square plus q dot by k is equal to 1 by alpha, the change in temperature with respect to the change in time, where alpha is the thermal diffusivity. So alpha is equal to k by rho times Cp. So if the condition are steady, then the change in temperature with respect to the change in time will be 0, and we'll consider this is in only one direction. So we get that is in x direction. So we get w/t by w(x) square plus q dot by k, which is equal to 0. And now what we need to do is we need to integrate this equation. So integrating this equation, we get w(t) by w(x). First we'll rearrange this equation. Okay, so w/t by w(x) square is equal to negative q dot by k. So then we need to integrate this equation. So integrating, we get w(t) by w(x) is equal to negative q dot by k times x plus c1. So integrating again, integrating, we get t is equal to negative q dot by k times x square by 2 plus c1 times x plus c2. So this is our equation number 1. And now what we need to do is, here we can easily identify that the temperature is the function of distance x and the nature is parabolic, because t is proportional to x square, so the nature should be parabolic. That means when the slab is maintained at the equal temperature, let's suppose that the left hand side the temperature is Ts, and as we are maintaining the slab at equal temperature, the temperature at the right hand side will also be equal to Ts. And now we know that the nature is parabolic, so this will be the nature of the temperature distribution. And now what we need to do is we came up with the equation t is equal to negative q dot x squared by 2k plus c1 times x plus c2. And now as we have two constants, so we need to take two boundary conditions. So our first boundary condition is when x is equal to 0, t is equal to ts, and let's suppose that the thickness of this slab is L. So when x is equal to L, t is equal to ts. So by making the use of the boundary condition 1, we know that ts is equal to, this will become 0, this will become 0, this will be c2. Let's call this equation number 2. And using the boundary condition 2, so we know that ts is equal to negative q L squared by 2k plus c1 times L plus ts. So this ts will get cancelled, so we'll get ql squared by 2k is equal to c1 times L, and our c1 is equal to ql by 2k. Let's call this equation number 3. Now we'll put equation 2 and 3 in equation 1 in this equation. So we'll get t is equal to negative q dot x squared by 2k plus c1 is ql by 2k times x plus c2 is ts. So we came up with this equation. And now what we need to do is we need to find the maximum temperature inside this slab. So in order to derive the maximum temperature equation in this slab, we will take the derivative of dt with respect to x, and then we'll put this equation equal to 0. So dt by dx, which will be equal to negative q by 2k times 2x plus ql by 2k, which will be equal to 0. So negative q 2x divided by 2k, which will be equal to negative ql by 2k. So this 2k will get cancelled, negative will get cancelled, q will get cancelled. So 2x is equal to L, x is equal to L by 2. Let's call it the equation number 4. Means the temperature is maximum when the distance is L by 2, and we have considered that the thickness of the slab is L. So at x is equal to L by 2 means exactly at the center the temperature will be maximum temperature. So now what we are gonna do is we are gonna put the maximum temperature in this equation, and then so Tmax is equal to negative q, x is L by 2, so this will be L by 2 bracket square divided by 2 times k plus ql, x is L by 2 divided by 2 times k plus ts. So what we are gonna do is, so Tmax is equal to negative q L squared by 4 times 2 times k plus ql squared by 4k plus ts. So Tmax is equal to negative ql squared by 8k plus ql squared by 4k plus ts. So this will be negative ql squared times 4k plus ql squared times 8k divided by 8 fours are 32k square plus ts. So this will be 4 times ql square k, ql square k, okay, divided by 32k square plus ts. So 88 fours are 32, 4 ones are 4, 4 8s are 32, and we have ql square by 8 times k, because this k is gonna get cancelled, plus ts. and here we have Tmax. So Tmax minus Ts is equal to QL squared by 8K. So the temperature difference between the maximum temperature and the surface temperature is QL squared by 8 times K. So this was all the information and all the equations regarding what happens when the slab is maintained at the same temperature Ts on left and right hand side. So thank you for watching this video.